So as I said the first time, what we are looking at is sketching parabolas in vertex form. We're going to have a look at what happens when I change the values of A, H and K in our turning point formula. So A, H and K, they're the ones that we're interested in. So I'll rewrite that formula so that we can see it, it's a bit clearer. So the turning point form that we are working with is y equals A multiplied by x minus h squared plus k on the end. So as I said, what I've set up at the start here, can I just get your scissors down? Can I get you tuning in? You're still chopping, it's very distracting. Thank you. I need you to listen, I need you to watch. The cutting paste activity, that'll be our exit ticket. Calm your farms. Right, Charlotte, put them down, put them down. That's it. Right, so this is our basic parabola. What I've done for this basic parabola is I have made A equal to 1, H equal to 0, and K equal to 0 as well. So when I do that in the equation, if A is equal to 1, H is equal to 0, and K is equal to 0, what I was trying to get to in the first place for the first version of this video that didn't work is that all I end up with is the equation y equals x squared. That is my basic graph. This one right here is what we call a parabola. Okay, it's the graph of y equals x squared. So let's start now by actually making some adjustments to the A value. What happens to the graph as I start to make A bigger? What can you see happening? What's changing? It's getting skinnier. What do you notice about the points? They're going up. So when A is 5, where are those points? At y equals 5. When A is 6, where are those points? Y equals 6. So when we change the A value, it's actually stretching our graph. It's stretching those points away from the x-axis. They're moving further away from the x-axis. So there's a formal word that we use for this stretch away from the x-axis. Starts with a D. Does anyone know what it is? It is called a dilation. All right, so this is where I want you to break out this little piece of paper here. Now, we couldn't decide in the last lesson, do you think the yellow one or the pink one is more pointing towards A? Yellow? All right, so in the yellow box, you're actually going to write what A does. And the A value is that big enough? Yeah. The A value dilates the graph by a factor of A units from the x-axis. Okay, so when we change A, it is dilating the graph away from the x-axis. So it's getting bigger, it's getting bigger. So when it was 1, that's our standard graph. As I go bigger than 1, we can say it's getting skinnier, we could say it's getting narrower, but if you write skinnier or narrower, I will not give you marks. What I want you to write is the graph is being dilated from the x-axis by a factor of whatever A is. So if A was 4, you'd say by a factor of 4. If A was 5, you'd say by a factor of 5. Now notice, what happens when A is between 1 and 0? What's happening to the graph? It's getting wider. This is still a dilation. What's the value 0.5 the same as? Half. So it's still dilated from the x-axis. by a factor of 1/2. But when I dilate from the x-axis by a factor of 1/2, it was up here. That factor of 1/2 actually brings it halfway closer to the x-axis. What's 0.1 the same as a fraction? 1/10. So when I have a equal to 0.1, it is 1/10 of the distance from the x-axis. We still say it's a dilation from the x-axis. We still say by a factor of a, whatever that is. What happens when a becomes 0? Why is it a straight line? 0 units away from the x-axis at all points. What happens to the equation when a is 0? If I put a 0 in here, makes everything 0. What's 0 times x squared? It's just 0. So we end up with a straight line graph, which is the graph of y equals 0. All right. Put my x squared back in there. When a is negative, wrong computer because I've got so much going on today, what happened to my graph? Okay, it's actually going away from the x-axis now in a negative direction. There is a formal word that we use for this. It's no longer a dilation. So I've set a to negative 0.5. I'll actually make it negative 0.1. We don't say that this graph's been dilated. It's not skinnier than the original y equals x squared graph. It's not wider than the original y equals x squared graph. So we don't talk about a dilation. But this is where you've got the second box on your little piece of paper. And if you want to change it so it sort of like points to the front a little bit more, that might make more sense. If there's a negative in front of the a value, what has that negative done to my graph? Someone said it before, Calder. Reflection. It is a reflection. Now, if there is a negative, what we actually have to write is the graph is reflected in the x-axis. Now in year 12 we do reflections in the y-axis. If you have a go at the past exam questions, you might come across one that's been reflected in the y-axis because the past exam questions are supposed to challenge you and push you and help you learn new things, so I don't apologise for that. But for year 11 in the curriculum, we're focusing on reflections in the x-axis. Notice, this language is important. We don't say it's a reflection on the x-axis. We don't say it's a reflection across the x-axis. We say it is a reflection in the x-axis. You do not say about the x-axis. All right, I want you to use the word in. The reason I want you to use the word in, because that's exactly how they write it in the study design, and then there's no debate about what you meant. All right? So we dilate by a factor of a units from the x-axis. Same thing, we say from the x-axis for the dilation. So if you're asked to explain what's happened to the graph, you'll break out this little piece of paper and you'll copy it word for word and just change the appropriate numbers. All right? Okay. Let's go back to a equals 1, our basic graph. Let's now have a look at what happens when I change the h value. And I know some of you have done this before, so you'll probably be okay with it and you'll tell me what happens straight away. When I change the h value, watch what happens to the graph. So ignore the k for a moment. What's going on with my graph? It moves along the x-axis. I heard somebody whisper in the front. It is definitely moving along the x-axis, isn't it? When h is 5, how far along the x-axis did it go? 5. If h is -3, how far along the x-axis did it go? Went to -3. So h moves the graph left and right. What's our word for moving the graph left and right? It starts with a T. It is a translation. Good. So, formal language. If we have H, again, pick the box that points to H. It's the green one up the top. Now, I'm kind of like squeezing it in this space because I think that's as far as the video actually shows that I'm recording for people who aren't here. But the H value, it translates the graph left and right. So, H translates the graph parallel to the x-axis. All right, if H is positive, which way did it go?
To the right.
If H was negative, which way did it go? It absolutely does go to the left. All right, but note, that is only when the rule, our formula, has a negative sign here. So if H is a positive, so for example, if H was 5, the equation actually says x minus 5. But the H value is what comes after the negative. H is what comes after the negative. So if my rule was y equals x plus 3 squared, then my H value is what comes after the negative. So I actually put 2 negatives in there to make it fit my vertex formula. And then that value there is my H. H would be -3. That graph would go to the left. Now, lots of students like to just remember if it's a plus, it goes to the left. If it's a minus, it goes to the right. And that will get you through 90% of problems. There are a couple of tricky questions where they'll try to confuse you in exams. To avoid that confusion, remember there's got to be a minus in vertex form. All right, and the H is what comes after the minus. Okay, I better speed up because I'm boring Kia. Now, moving along, K value then, it moves it on the y-axis. Now, what's the word for moving it? Sorry?
Translation.
It is a translation. So the K value translates the graph up and down. So, same thing with the language. K translates the graph, again, parallel to the y-axis. So if K is positive, it goes up. If K is negative, it goes down. All right, so if you're ever asked to describe these transformations, break out this piece of paper and write it down exactly like I have just explained here. This is what you need to write. If you want to play around with that graph yourself and get a better understanding, it is in the lesson slides which you have access to. Just click on the link, play around with your A, H and K and have a look at what happens. There's also a simple little widget here that's kind of showing you a few examples as well. All right, we're not going to do all of them. There should be one example here. Where's my one example? All right. My one example that I was going to do first doesn't look like it's there anymore. I'm just having a wonderful lesson where everything's going wrong, so that's okay. I think I might have accidentally deleted a slide. Let's have a look at this example for sketching, and then we're going to have a go at that piece of paper that I started making you cut, and that'll probably be the end of our lesson today because there's so many interruptions. Can I rub that off? Is anyone still madly writing? Okay. So what you folks need to be able to do is sketch graphs using that information. Okay, so if this is my equation, what are we going to put this as a heading? We're going to put this under the heading of sketching in vertex form. You can put it straight in your summary or in your workbook. As I said, you've got to work out where you're going. This is going to be an easy example. For some of you, it's too easy for what you need to have in your summary journal. But if you want to put it straight in there and have the easiest example possible, you'll have something. But I keep trying to say, like, don't just do this one example and then never put another example that's relevant to you. Okay, when we do these graphs, we're going to follow the DIRT principle. This is the DIRT principle. The I means absolutely nothing. It's only in there to help you remember DIRT and then maybe remember this process. Just because DIRT sticks in your head. It still says DIRT in my mind. So, no I, just DIRT. The first thing we're going to look at is, does our graph have a dilation? No dilation. Nil. How do you know? There's no number here. In fact, there is an A, it's just that it's 1. 1 doesn't count as being a dilation. All right? So, you're correct. There is no dilation. Is there a reflection? What causes a reflection? Negative. Is there a reflection? No. No, there is not a reflection. How do I know? There's no negative sign. Is there a translation? Yes, there's 2. What are those 2 translations? Let's start with H. Let's use the correct language. It is translated 3 units right parallel to the x-axis. It'll go right because my h value is 3.
You confused me with saying that thing before.
All right, there's a minus sign.
The other way around.
There's a minus sign. The h value is 3. It goes to the right to 3 places.
Yeah.
All right. So it's translated 3 units right. What's the second translation?
2 units up.
2 units up. So we say translated 2 units up parallel to the y-axis. So let's think about our graph. What's actually been translated? What's actually been moved here? Well, let's actually have a look. Let's go back. So we've got h is 3, y is 2. Oh, can't get 2 there. I'm getting there. Now the turning point absolutely has been translated. But what else has been translated? It's not just the turning point. The whole graph goes up 2 places. Every single point on that graph goes up 2 places. Every single point on that graph goes to the right 3 places. The shape, I know it looks like the dots are rolling, just ignore the dots rolling for a second. But the whole graph has been shifted 3 places to the right. It's exactly the same shape. But if we know that the whole graph's gone 3 places to the right and 2 places up, then absolutely We know the turning point has the coordinates 3, 2. What else do you think would be an important point to mark on this graph? How else do I show that there wasn't a dilation? Say it again over here. The y-intercept. So in order to show that there was no dilation, or in some cases there was a dilation, we need to get another point on there. And the points that we try and show are our vertex, our y-intercept, and our x-axis intercepts, if there are any. How do I find a y-axis intercept? I can hear people whispering it, but while others are thinking, I'll give you a hint. I know the coordinates for this point are 0 something. In order to find the y-axis intercept, we're going to substitute x equals 0 into our equation because we know that x is equal to 0 at that y-intercept. So the y-axis intercept, sub x equals 0. What does that look like? I replace the, oops, that was a minus sign. I replace the x with 0. So what's 0 take away 3?
Minus 3.
Square it.
9.
Plus 2.
11.
So that would be my coordinates. All right, I think you guys need to do some work rather than listening to me, but we're not going to have time. So, sorry for the messed up